In the modern era of agricultural warfare, the standard response to a pest invasion is usually chemical supremacy. Fleets of aircraft blanketing the earth with potent neurotoxins. Yet, when faced with a catastrophic locust plague in the arid expanse of Xinjiang, China, a global technological superpower chose to ignore industrial logic. Instead of deploying drones, they deployed a military unit comprised entirely of 100,000 flightless birds. This was not a primitive desperation move. It was a calculated strategic counterstrike. A disciplined column of Shaoxing ducks was marched into the kill zone to intercept a locust swarm capable of devouring thousands of acres of pastureland per day. The authorities had run the numbers. They realized that a chemical strike was a sunk cost, expensive to deploy and ecologically suicidal for the grazing land they were trying to protect. Instead of spending millions on single-use poisons, they utilized soldiers that actually gained market value with every enemy they consumed. They didn't just stop the plague. They converted a biological crisis into a profitable protein harvest. But from an engineering standpoint, the math seems impossible. How does a single biological organism physically outperform a liter of industrial pesticide in terms of sheer efficiency? To understand why a biological solution became inevitable, we must first look closely at the enemy itself. Locusta migratoria, the migratory locust, is not just an insect. It is one of nature's most efficient agents of destruction. According to data from the UN's Food and Agriculture Organization, a single square kilometer can hold as many as 80 million locusts when a swarm reaches peak density. Each individual may seem insignificant, but biology has honed it into a near-perfect eating machine. Every day, a locust consumes roughly its own body weight in vegetation, about 2 grams. On its own, that is trivial. Together, it is catastrophic. Scale this up and the numbers quickly become overwhelming. A swarm covering just 40 square kilometers will consume around 6,400 tons of plant matter in a single day. That is the daily food requirement of roughly 35,000 people. In the open pasturelands of Xinjiang, the swarm behaves less like an animal population and more like a moving wildfire, stripping the land to its roots. Yet the true threat lies not in what the locusts eat, but in how they multiply. Locust populations obey the logic of exponential growth. One female can lay up to 100 eggs in a single cycle. If chemical pesticides destroy 90% of a swarm, the remaining survivors suddenly face less competition for food. Within weeks, their numbers can rebound to previous levels. The land may look quiet for a moment, but the clock has merely been reset. So why not overwhelm them with chemicals? In theory, industrial pesticides promise a swift solution. In reality, the vast steppes of Xinjiang make conventional approaches unworkable. The terrain is uneven, rocky, and immense. Ground vehicles cannot traverse it efficiently, while aerial spraying comes at a heavy price. Pesticides are expensive. Aircraft fuel, pilots, and chemical agents cost millions. The land being protected is grazing pasture, not high-value crops. If the cost of treatment exceeds the economic value of the grass itself, the outcome is the same whether the locusts survive or not. Farmers lose. Entire regions bleed money trying to save land that cannot repay the cost of its own defense. There is another cost, less visible but more lasting. Chemical sprays do not discriminate. They kill locusts, but they also kill beetles, birds, frogs, and other predators that form the ecosystem's natural line of defense. By stripping the land of life, pesticides weaken the system meant to keep locusts in check, leaving it even more vulnerable to the next invasion. Faced with this reality, Chinese agricultural engineers realized they were fighting a war they could not win through attrition. They did not need another chemical weapon. They needed something that could move freely across rough terrain, operate independently, and hunt continuously. They needed a solution that could turn the enemy itself into energy. They immediately thought of chicken and duck. First, let's analyze the psychological architecture of the two species. Chickens operate on a loose, selfish survival instinct. They are prone to scattering. When faced with a threat or a sudden noise, a group of 1,000 chickens will disperse in 1,000 different directions. In a vast desert environment, This makes them uncontrollable. They also possess a rigid circadian limitation. As soon as the sun dips, chickens instinctively roost and become immobile. They are, in military terms, cowards that require high-maintenance supervision. Ducks, conversely, possess a rigorous flock instinct. They are naturally disciplined. A single human handler with a whistle and a flag can command a unit of 5,000 ducks, moving them in a tight phalanx formation across the landscape. They stay together, they move together, and they attack together. This swarm behavior allows the handlers to direct the weapon precisely to where the locust density is highest, ensuring a 100% sweep rate of the infested area. But the most critical metric is dietary mechanics. In terms of raw processing power, the chicken is inefficient. An adult chicken has a consumption cap of approximately 70 locusts per day. While helpful, this volume is insufficient to break the reproductive cycle of a megaswarm. The duck is a metabolic furnace. A single adult duck can consume over 200 locusts per day. That is nearly a 300% increase in efficiency per unit. Furthermore, ducks have a unique digestive system that allows them to process the hard, chitinous exoskeletons of locusts more rapidly, converting that biomass into immediate energy for movement. When you multiply this by 100,000 units, the difference is staggering. A chicken army removes 7 million pests a day. A duck army removes 20 million. That gap of 13 million locusts is the difference between saving a harvest and losing it. Then there is the issue of durability. Xinjiang and the border regions are hostile environments. Scorching days, freezing nights, and wetlands mixed with arid scrub. Chickens are biologically fragile. They dislike wet conditions and are susceptible to respiratory diseases when exposed to dust and dampness. Ducks are amphibious all-terrain vehicles. Their plumage is waterproof and insulated, allowing them to forage in rain, mud, or marshland without suffering thermal stress. They can march for miles without exhaustion. This durability enables what strategists call the pincer strategy. Aerial sprays have a major flaw. They only kill the adults on the surface. They cannot penetrate the soil. The duck's bill is a specialized tool, a sensory-rich shovel. Unlike a chicken's beak, which pecks precisely at the surface, a duck's flat bill is designed to root and dredge. As the duck wave moves across the field, they don't just snatch flying locusts. They dig into the earth. They hunt the pupae and larvae hidden centimeters underground, the bunker population that chemical sprays miss. This is a double-tap strike, destroying the current army and the future generation simultaneously. To execute this, China utilized a specific hardware specification, the Shaoxing duck or Anas platyrhynchos domesticus. This is not your average pond duck. The Shaoxing breed has been genetically refined over centuries in Xinjiang province for specific traits that make it the perfect biological weapon. 1. Size to agility ratio. Adults weigh approximately 1.5 kilograms. They are heavy enough that they cannot fly away, securing the inventory, yet light enough to run rapidly across uneven terrain. 2. Aggression. This breed has a high foraging drive. They do not wait to be fed. They hunt. 3. Production value. A female Shaoxing duck can lay up to 300 eggs per year. This ensures that the weapon has a secondary economic value beyond pest control. Finally, we arrive at the loop of logic that makes this system a masterpiece of pragmatic engineering. In a chemical war, you constantly burn money to destroy the enemy. In this biological war, the enemy becomes the fuel. The locusts are high in protein, approximate 62% dry weight. As the ducks consume the swarm, they convert that pest biomass into muscle and egg production. The more they fight, the stronger and more valuable they become. It is a self-sustaining combat system. The farmers do not need to buy feed. The enemy provides it. The ducks do not need to be refueled. They refuel themselves. By the end of the campaign, the soldiers are significantly heavier and ready for market, turning the very biological mass that threatened the region into a harvestable asset. This is the ultimate efficiency, using the problem to feed the solution. When the dust settled on the Xinjiang pastures, the data vindicated the biological strategy. The deployment of this 100,000-strong bioarmy did not just suppress the invasion. It executed a total ecological scrub of the affected zones. Let's look at the hard kill data. With a verified consumption rate of over 200 locusts per duck per day, the entire fleet was neutralizing approximately 20 million locusts every 24 hours. Over a standard 60-day campaign season, that equates to a staggering 1.2 billion pests permanently removed from the ecosystem. This massive reduction successfully created a defensive buffer around 3.8 million hectares of critical agricultural land. Specifically, they protected the region's vast fields of alfalfa, lucerne, and winter wheat, crops that serve as the nutritional backbone for China's livestock industry. Without this intervention, experts estimated that 30% to 50% of this biomass would have been stripped to the stalk within weeks. But the most impressive metric isn't what was removed, it's what was added. In a traditional chemical campaign, the pesticide residue sterilizes the soil, killing beneficial microbes and risking groundwater contamination. The duck battalion did the exact opposite. As they marched, 100,000 ducks deposited tons of nitrogen-rich manure directly onto the grazing land. They were simultaneously weeding the fields and fertilizing them. This effectively closed the nutrient loop, accelerating the regeneration of the grass that the locusts had damaged. Now, let's talk about the return on investment. This is where the duck model leaves modern engineering behind. At the start of the campaign, the ducks were young and lean. The locusts, which contain roughly 62% protein and 17% fat, served as a high-grade, free feed source. In a factory farm, feed accounts for 60 to 70% of the total production cost. Here, the feed cost was zero. By the end of the operation, the biological assets had appreciated in value. The ducks had grown significantly heavier and healthier due to the organic, high-protein diet. Once the locust threat was neutralized, these veterans were not discarded like empty pesticide canisters. They were harvested. The males were sold into the meat market, fetching premium prices as free-range, organic poultry. The females were retained for egg production. A single Shaoxing duck can lay up to 300 eggs per year, creating a long-term passive income stream for local farmers long after the locusts were gone. When we run the final cost-benefit analysis, the difference is stark. According to reports from the Xinjiang Academy of Agricultural Sciences, the cost of chemical spraying in this terrain averages about 100 renminbi per hectare. In contrast, the biological duck control costs roughly 30 renminbi per hectare. This means the biological method is 70% cheaper than conventional chemical warfare. Chemical model, you spend $1 to save $2 of crops. Net gain, $1. Duck model, you spend 30 cents to save $2 of crops, plus you gain $1 in meat/egg sales. Net gain, $2.70. The data is irrefutable. Xinjiang authorities didn't just solve a pest problem. They turned a potential famine into a localized economic boom. They proved that, in the right context, a biological stomach is infinitely more efficient than a chemical tank. However, as successful as this operation was, we must look at the bigger picture. Can this model scale globally, or is it a one-time regional anomaly? In the final section, we will analyze the geopolitical ripples of this project and why China considered sending this air force abroad. The success of the Shaoxing battalion was so profound that it transcended mere pest control and entered the realm of international diplomacy. In early 2020, when China's strategic ally, Pakistan, declared a national emergency due to a massive locust invasion, the Chinese government didn't just offer money or chemicals. They prepared an avian expeditionary force. State media reported plans to airlift 100,000 ducks from Xinjiang to the Pakistani border. This was a moment of agricultural soft power, using biological assets to strengthen geopolitical alliances. It demonstrated that in the face of food insecurity, a sustainable biological solution holds as much diplomatic weight as a shipment of advanced weaponry. However, as we analyze this case study, we must remain intellectually honest about the limitations. The duck model is not a magic bullet for every scenario. First, there is a hydrological constraint. These are ducks, not camels. They require access to water for thermoregulation and hygiene. In the severe, bone-dry droughts often associated with deep desert locust breeding grounds, a duck army cannot survive without a massive, expensive artificial water supply chain. Second, this is a ground war solution, not an anti-aircraft one. Ducks are effective against hoppers or juvenile locusts and adults on the ground. Once a swarm takes flight, becoming a cloud of millions moving at 20 kilometers per hour, the ducks are helpless. You cannot deploy infantry to fight an air raid. In those late-stage scenarios, aerial chemical intervention remains the only grim option. But the existence of these limitations does not diminish the core lesson of the Xinjiang experiment. We live in an age where we are obsessed with high-tech. We tend to believe that the solution to every problem involves silicon chips, artificial intelligence, or synthetic chemistry. But the Shaoxing duck is a reminder that technology doesn't always mean circuits. Evolution has spent 100 million years performing research and development to create the perfect locust-killing machine. It is self-replicating, solar-powered, or via grain, and biodegradable. The Chinese engineers didn't invent a new solution. They simply recognized that the most advanced technology on Earth wasn't built in a lab. It was hatched. This forces us to rethink the future of agriculture. As chemical resistance grows and soil health declines, perhaps the next great leap forward isn't about inventing new poisons, but about rediscovering the ancient, brutal efficiency of nature's own food web. So, here is the final question for the community. Do you think biological control, like these ducks, is scalable for modern, massive commercial farming? Or is this just a niche solution for remote areas that can't afford chemicals? Let us know your verdict in the comments below. If you enjoyed this deep dive into the strange world of extreme agriculture, please hit the like button. It helps the algorithm find more people like you. And make sure to subscribe to the channel so you don't miss our next breakdown of the world's most impossible engineering projects. Thanks for watching, and I'll see you in the next field.